All right. Let's suppose you've got an oblique triangle and you set it on one side so that it has a base. In this case, I have that base labeled B with angle B opposite that. Let's take that and let's put an altitude down from this point here. This is like the height. We were in the last section we were just working with those area formulas, and we called that height. In this example, actually, I'm going to go ahead and call that variable y. Okay. Then I'm going to look at two triangles. I'm going to look at the triangle on the left and the triangle on the right. All right. So we're splitting this up into two pieces. Those two triangles are both right triangles. So I can do regular trigonometry with ratios on each of those triangles individually. Let's highlight them with two different colors. We've got the red triangle on the left. Okay. And then we've got the purple triangle on the right. There we go. And that's also, they're both right triangles. So for the length B here, this length B is split into two pieces right here, right? So what we want to do is relabel each side of that. And I'm going to go ahead and label this side over here X, kind of corresponding with the Y. We've got X and Y as the legs of this red triangle. And if the whole length is B, but that portion of it is X, then this portion over here is going to be B minus X. So now what I'm going to do is I'm going to do some trigonometry on each of the two triangles. Let's start with the red triangle. On the red triangle here, if I take angle C in the corner here, if I were to do the cosine of C, I would get adjacent over hypotenuse, which in this example is going to be x over a. Okay, so adjacent divided by hypotenuse. So this means that that x value, that x distance there, is a times cosine of angle C, like that. Well, that's useful. It's the side A times cosine of this. Sine of that angle C is, of course, y over a, so that gives us that y is a times the sine of C. Okay, so now from the red triangle, we have obtained formulas for x and y in terms of the sides and angles of the triangle overall, like the overall oblique triangle. Now we're going to turn our attention to the purple triangle. And on the purple triangle, instead of doing trig, what I want to do here is use the Pythagorean theorem. Okay, and this isn't like, I'm just not just making this up. This is coming from somewhere. We're heading somewhere here. Okay. So we're going to use the Pythagorean theorem on this. We're going to take the legs of the triangle, b minus x and y. We're going to square each of those and add them together, and that should give me the square of the hypotenuse, which is c. So that equals c squared. So there we go. So now if I square this out, if I actually multiply this out, I get b squared minus 2bx plus x squared, and then plus y squared equals c squared. Like that. Now, x squared plus y squared, by the way, since the Pythagorean theorem could apply to the left triangle as well, x squared plus y squared is just going to equal a squared, right? So this portion of it right here is going to boil down to just plus a squared. So I've got that. Now, let me just write the rest of it in here. So far I have this. Now the x here, for x we could use this formula. A times cosine of c. So we're going to take the a times cosine of c and go ahead and stick that in for x. I'm going to pull my a squared out to the front. So I've got a squared plus b squared here. And then I have minus 2b times x, which is a cosine of c. And this all equals c squared. And what I've obtained here through these steps is something that we call the law of cosines. So let's bring this up here. Law of cosines, one version of it is c squared. This is side c. C squared equals a squared plus b squared minus 2 times a times b times cosine of the angle that's opposite the side we started with, angle c. Now, that version of the law of cosines involves the three sides a, b, and c, and only one angle C over here, and it uses the cosine. That's why it's called the law of cosines. It involves the cosine. We could rearrange this. If you wanted to put it in terms of b, you could do b squared equals a squared plus c squared minus 2ac times cosine of the angle which is opposite b, which would be capital B. And then we could put it in terms of a squared, get b squared plus c squared minus 2bc cosine of angle A. And we could do the proof that we did on the left side here. We could have rearranged this, like if we rotate the triangle and use a different y, like rotate and use a different, each time using a different altitude, we can get all three versions of this, by similar sort of reasoning. Okay, so these are three versions which are all different versions of the same law, the law of cosines. There's also something you can do with these where if you solve for the cosine of the angle, whatever that angle is, then you can kind of rearrange these formulas into something which is useful if you're trying to solve for an unknown angle. So the first formula, if you solve for cosine of c, you end up getting a squared plus b squared minus c squared divided by 2ab. So that is a useful version of the same formula which you can use if you're trying to get c. You can take this, calculate this, which uses all three sides of the triangle, and then do an inverse cosine to get the c value back again. The version of it for b looks like this: a squared plus c squared minus b squared over 2ac. And the version for a looks like b squared plus c squared minus a squared over 2bc. So there's patterns here, and if you memorize one of them, if you memorize one of these and one of these, then you can figure out the other ones by just kind of permuting or sort of swapping around the different letters so that they play the correct roles. All right, so here's our law of cosines. We're going to use this in a couple of examples.